Welcome to the Hubble Space Telescope Public Lecture Series. Today's talk, the Hubble Space Telescope, From Cosmological Conflict to Alien Atmospheres by Tom Brown. We're at the Space Telescope Science Institute, and I am Dr. Frank Summers as your host. I'd like to thank our wonderful tech team, Thomas Marufu and Grant Justice, who help us bring you this live stream every month. Next month, we will have a really special talk from author Christopher Wanjek, who will be talking about spacefarers, how humans will settle the moon, Mars, and beyond. This is a little different talk for our series, and I know you won't want to miss that one. In May, we have another special talk from the Consonance Collective and the Bergamot Quartet of the Peabody Institute here in Baltimore. This is an orchestra, and these are musicians who are going to talk about and play for you Finding the Music of the Spheres, Hearing Stars. And finally, in June, we will have a talk on exoplanets. That's not the final title. She promised she would give me a different title soon, by Emily Rickman here at the Space Telescope Science Institute. If you'd like to learn about it, you can go to our website. Just go to www.stsci.edu/public-lectures, and you'll find this webpage. On the lower left is you can find things about our webcasting, both on the YouTube playlist and the webcast archive from the Space Telescope Science Institute. On the lower right, you can see our email, on which you can enter your email address and subscribe and get our monthly postings. Also on the website, we have descriptions of each lecture, both in compact form, and if you click on it, then of course you get the full details along with the title, the description, as well as links to the STSCI webcast and the YouTube version of the webcast after the recording. For the email, the announcements, it's easiest just to sign up at our website. You can also subscribe to our YouTube channel, youtube.com/Hubble Space Telescope, all one word. That will give you notices of these live events as well as notices of new videos. And finally, if you have comments or questions, you can send them to the email address publiclecture@stsci.edu. Our social media. We have social media for the Hubble Space Telescope, for the James Webb Space Telescope that launches in October of this year, and for our Institute, Space Telescope Science Institute. We're on Facebook, Twitter, YouTube, and Instagram. As for myself, I do a tiny bit of social media, both on Facebook and Twitter. And now, the news from the universe for March 2021. Our first story for you tonight, a comet amongst the Trojan asteroids. Now, that actually is a lot more different, strange than it may sound. So let me just break down what we're talking about. First of all, this is a diagram of the inner solar system, okay? And it's out to the orbit of Jupiter. And what you can see, the main thing in red is the main asteroid belt. There are hundreds of thousands, 300, 400,000 asteroids in the main asteroid belt. And you can see they stretch mostly from the orbit of Mars out to the orbit of Jupiter. And of course, interior to the orbit of Mars are the orbits of Venus, Earth, and Mercury. Now, there's also these blue objects that are in that realm, and these are what we're called the Mars crossing asteroids. And they look like they could really cause havoc to us, but really there aren't that many of them, and they're really, really small, so they aren't that much of a threat as it may appear in this diagram. But what I really want to talk about are these green blobs in the upper left and the upper right. These are what's called the Trojan asteroids around Jupiter, and I've marked at the top where Jupiter exists. And you'll notice that there's a clump of asteroids about 60 degrees in front of Jupiter and 60 degrees behind Jupiter. And that's because the gravity of the Sun and Jupiter sort of balance out to create these semi-stable points, 60 degrees in front and 60 degrees behind Jupiter. And the asteroids can sit there and hang out there. So it was kind of crazy when Hubble took this recent image of a Trojan asteroid. This is the Trojan asteroid 2019 LD2. And you may look at that and go, wait a minute, that doesn't look like an asteroid. No, it doesn't look like an asteroid. It's got a tail. What has tails? Comets. This isn't an asteroid. This is, in fact, comet P 2019 LD2. And then you might ask, well, okay, so what is a comet doing hanging out in a place where there are asteroids? Matter of fact, this is the first comet ever discovered hanging out in a place where there are asteroids. And to tell you that, I got to go give you the bigger picture of the outer solar system. So here's a plot of the outer solar system. And the main feature here is the Kuiper Belt, all these red and white objects around the edge outside the orbit of Neptune. That is the Kuiper Belt. Now, if you haven't heard of that, this is a region of the solar system that we only discovered in the 1990s. And we know thousands of objects out in the Kuiper Belt. These are small, icy bodies out at the edge of the solar system. And by the way, this is the region that includes Pluto. This is why Pluto is no longer a planet, because it's actually a member of the Kuiper Belt. But let's not get into that because people can talk your ear off about that. So what happens is the Kuiper Belt is the repository of these small icy objects that, if they get pulled into the inner solar system, become comets. So they can have gravitational encounters with Neptune and with Saturn and Uranus and Jupiter that can bring them into the inner solar system. And so when they are traversing between the orbits of Neptune and the orbits of Jupiter, there's something known as centaurs. So there's this sort of gravitational pinball that happens with these Kuiper Belt objects. So the significance of seeing comet P 2019 LD2 in the Trojan asteroids is that it is assuredly a comet that has been pulled in by this gravitational tug of war. Sometimes they call it a bucket brigade, as one planet hands it off to the other planet and moves it in. And it must have had a close encounter with Jupiter relatively recently that pulled it into a place where it could be part of this semi-stable pack at the Trojan asteroids. But it doesn't really fit in with the Trojan asteroids within its orbit. The cool thing is they do simulations of this on how long it will last there. Probably within a few years, we will be able to watch LD2 move out of the Trojan asteroids and change its orbit. We can see orbital dynamics happening on a timescale of several years. Now, maybe it will come into the inner solar system, and maybe it'll be a bright comet we can see in the night sky. But actually, probably not, because they predict that within 500,000 years, there's a 90% chance that it will have a gravitational encounter with Jupiter that, instead of sending it into the inner solar system, will actually kick it out of the solar system. So this is the first comet discovered amongst the Trojan asteroids. Is it a standard way station on the traveling in from the Kuiper Belt to the inner solar system? Possibly. They will continue to look for more and will be able to follow the development of comet LD2 within the next decade. Second story, I'm not going to go very deep into because many of you have probably seen a lot of it already. This is Perseverance on Mars, okay? If you didn't know, if you're living under a rock, Mars 2020 mission called Perseverance has landed on Mars. And here are several pictures. In the upper left, that is the parachute that they use to glide it down to the surface. And let me note that the parachute is designed to work in a very thin Martian atmosphere. And so they really couldn't test it on Earth with our much thicker atmosphere. So that's an amazing feat of engineering, because they really couldn't test it in advance in the conditions. And then you've got the shot looking down on the rover as it's heading to the surface, the shot of the rover on the surface, and three cool panoramas. There is a ton of cool information. And if you haven't watched the descent and landing video, You got to check it out, okay? Mars Perseverance, we're going to get some interesting science from the crater, trying to look for signs of life. Could life have developed in this crater that was once an ancient ocean? That's stuff to stay tuned for. But for right now, you can get some really cool new images from Mars. Okay, to our featured speaker tonight. Our featured speaker tonight is Tom Brown, and he is an extremely important person. He is the head of the Hubble Mission Office here at the Space Telescope Science Institute. He got his undergraduate degree at Penn State, then got his did his graduate work across the way at Johns Hopkins University. He went down to our partner institution, the Goddard Space Flight Center, and then came here to Space Telescope. And it's fun that Tom and I learned today that we've both been at the Space Telescope Science Institute for 20 years now. So we're both celebrating our 20th anniversary at Space Telescope this year. He's going to tell you all about what his functional work is, but he also does research. This is a guy in a really important position, but he's still doing his research. Matter of fact, he was telling me he just got Hubble data last night on the globular cluster M4, and he's just itching to preview that data and study it. So without further ado, ladies and gentlemen, Dr. Tom Brown.
Thank you, Frank. All right, hello everyone.
Yeah, thanks. As you heard, my name's Tom Brown, and I work at the Space Telescope Science Institute, and I'll be talking to you today about the wide range of science with the Hubble Space Telescope. So Hubble was launched over 30 years ago in 1990 as a partnership between NASA and ESA, and it's become increasingly powerful over the years through a series of servicing missions. 3 missions in the 1990s, and then another one in 2002, and another in 2009. And while there are no additional servicing missions planned, the observatory is expected to be scientifically operational through at least 2026, and hopefully the entire decade. This is an overview of the physical characteristics of the observatory. It's about the size of a school bus. It's a little over 13 meters long, 4.2 meters wide, a weight of 12,200 kilograms. It's a Cassegrain telescope with a primary mirror 2.4 meters across, a secondary mirror 0.3 meters across. It's in orbit at an altitude of 536 kilometers and goes around the Earth once every 95 minutes. And the orbit's expected to be stable into the 2040s. The power is provided by solar arrays on the day side and batteries on the night side, and it consumes 2,100 watts of power. The Hubble Instrument Suite, which is shown in their layout here on the observatory, provides unique capabilities that keep the telescope in high demand and also keep it on the cutting edge of astrophysical research. I'll go through those briefly here. First, there's the Cosmic Origin Spectrograph, or COS. It was installed in the last servicing mission in 2009, and it's optimized for ultraviolet spectroscopy of faint sources. Complementing those capabilities is the Space Telescope Imaging Spectrograph, or STIS. It was installed in the late 90s and repaired in the last servicing mission. It provides versatile spectroscopy and imaging over a broad wavelength range in the optical, ultraviolet, and near-infrared. Next is the Advanced Camera for Surveys, or ACS. It was installed in 2002 and repaired in the last servicing mission. It provides wide field imaging and spectroscopy with an emphasis on red sensitivity. And then there's the Wide Field Camera 3, which was installed in 2009, and it provides wide field imaging and spectroscopy with a broader wavelength range extending into the ultraviolet and the near-infrared, and also astrometric capabilities. Last, there's the Fine Guidance Sensor Package, or FGS. It was launched with the telescope. It has 3 sensors, 2 of which were refurbished on subsequent servicing missions. It's mainly used as part of the point and control system, but it can also be used for astrometric science. The diagram I'm showing on the right shows the 2 main types of data that you get from these instruments. This is looking at the massive star Eta Carina, and this star system is quite violent. It's shown here as a Hubble image on the left side of the diagram, a high-resolution Hubble image, And then a spectrum from the center of this object is shown extending along the right side of this diagram. And this demonstrates all in one diagram the power of the Hubble Space Telescope. Hubble has powerful imaging and spectroscopic capabilities. They extend in the ultraviolet, the optical, and the near infrared. And the ultraviolet is particularly important because you can't do ultraviolet astronomy from the ground due to the opacity of the atmosphere. And the atmosphere also blurs light at other wavelengths, and Hubble avoids that by being in orbit. And Hubble has high resolution and contrast in its imaging and spectroscopy. And these capabilities make Hubble a powerful facility still to this day. You can see the spectrum here complements the information you obtain with the image because of the features in the spectrum corresponding to the chemistry of this object. So first, I'm going to review how powerful these two cameras are. These cameras are far more powerful, the ones that are on there now, ACS and Wide Field Camera 3. They're far more powerful than those on previous generations on the Hubble. So what I'm showing here on the left is the Hubble's 30th anniversary image of the cosmic reef. This is a beautiful image. I'm going to step through a series of Hubble images of nearby galaxies to make a point. So these are mostly spiral galaxies like our own Milky Way, spiral galaxies in the nearby universe. And all these images are quite beautiful and the subject of press releases with the telescope. And some of these are thought to look somewhat like our own Milky Way, and there are pairs of galaxies and interacting galaxies. But I'm going to zoom in here on the Sombrero Galaxy. So the Sombrero Galaxy is beautiful edge-on galaxy here. You can see this prominent dust lane in the foreground. But what's fascinating is that you don't just see the Sombrero Galaxy, you see much of the universe behind the Sombrero Galaxy. And I can zoom in here. You can see that there are distant spiral galaxies in the distant universe behind the Sombrero that are also in this image. And that's something that really started to become common with these two most powerful cameras we have on there most recently. Previous generations of cameras didn't exhibit this behavior, but now when we get an image with Hubble, we get not only the object we're looking at, but we tend to get much of the universe behind that object for free in the same exposure. That's because these cameras are so powerful. Now, a lot of the science in Hubble comes from its spectrographs. I mentioned there are two spectrographs in Hubble that complement each other, COS and STIS. Now, press releases on science results involving the spectrographs often involve an artist impression because you don't usually get a pretty picture with this type of science. I'm going to show you in this talk both the artist impression for those cases, but I'm also going to show the spectroscopic data. And I'm doing that just so those viewers who are interested can see the scientific data alongside the artist impression. And briefly here, I'll show you schematically how this works. You have a patch of sky with an object of interest. So this target star here is shown by the blue box. The light falls down the telescope, and most of it is intercepted, but the light from the object of interest falls through to a dispersive element, and then, or like a grating or a prism, and then is spread out on the detector where you get a pattern of light and dark corresponding to the chemistry and temperature in this object. And that spectrum is then transmitted back down to Earth. So how does this work in practice? So here are the Hubble data for the Southern Crab Nebula. This is an image obtained with Hubble as part of the 29th anniversary. And what I'm going to do here is show you also the spectrum obtained with Hubble for this object. So here is the Hubble spectrum. The light's dispersed with blue wavelengths on the left, redder wavelengths on the right. And then the features you see in the spectrum correspond to the chemistry of the object. So on the left here is oxygen, and then you also have hydrogen, nitrogen, and sulfur. And then those combine together to give you the colors you see in the actual image. So this object we obtained both imaging and spectroscopy, and you can see how those two types of data complement each other. The image tells us about the structure of the object, but the spectroscopy tells us about the temperature and chemistry. Now here are those data again, the images and the spectra of this object. Now I'm showing along the bottom the type of plot that astronomers typically show when they have a spectrum. So this is a plot of flux or energy on the y-axis versus color on the x-axis in nanometers from 500 to 700 nanometers. And you can see that the features in this plot along the black curve here, the spikes correspond to features in the beautiful outreach figure. So most of the time when astronomers have a spectrum they're showing in their paper, they show something like the plot along the bottom here, but you can see that the information in this plot corresponds to what's in the outreach image. Now, Hubble science spans the full breadth of astrophysical phenomena. That's shown here by this pie chart on the left. This is the breakdown of science topics in a broad brush that are being pursued by Hubble in the current observing cycle. Observing cycles occur on an annual basis, and you can see Hubble is doing work on black holes, it's doing work on exoplanets and planet formation. About a quarter of the time is going into galaxies. Significant amount of time is going to studying the dark material between the galaxies, the intergalactic and circumgalactic medium. We have cosmology and large-scale structure, the solar system, stellar physics, and stellar populations or groups of stars. Now in the upper right, I'm showing a plot of the number of refereed publications using Hubble data to date as a function of time over the history of the mission. And you can see that this is the scientific productivity of the telescope has really grown over the years, and now there's roughly 1,000 peer-reviewed papers per year, over 18,000 publications to date. And the bands of color in this plot show where the paper is drawing the Hubble data from. So the lowest band here in a greenish yellow color, those are papers published by the same team of astronomers who requested time on the telescope. So they asked for a time on Hubble, they got the data, and then they published their results. And then the bands of color above that are from teams of astronomers who went back into the archive, and at least part of their paper is drawing upon archival data collected from previous observations, not observations they requested themselves. So you can see over half of the data published with Hubble these days was drawn from the archive. Now, observing time on the telescope is awarded by a peer review process that's dual anonymous. That was an innovation that Hubble began in the field a few years ago. The Hubble telescope was the first telescope to use a dual anonymous peer review system. So the people submitting their ideas for peer review don't know who will be reviewing them. And then the people who are evaluating those ideas don't see the identities of who submitted the proposal. Those have been stripped from the proposal. And that allows the peer review to just focus on the science, and it mitigates bias in the review. The telescope remains in high demand. The oversubscription, whether you're measuring that by the number of requests for time or the amount of observing time needed, exceeds what's available in any given year by more than 5 to 1. Now, Hubble science evolves with the field. I'm going to show that here through two science topics that get a lot of attention these days. And the top is cosmic expansion. Now, the universe has been known to be expanding for decades. And when the telescope launched in 1990, astronomers hoped to use the telescope to accurately characterize the rate of expansion for the universe. What was not known when the telescope launched was that expansion of the universe had a period of both deceleration and acceleration. And Hubble played a key role in characterizing that variation in the expansion of the universe, and it was the subject of a Nobel Prize, along with other telescopes that were used. We are now in an era of precision cosmology, where people are measuring the expansion rate of the universe using different methods, and those methods don't always give the same answer within the uncertainties, and that might be implying new physics. And the bottom here, I'm showing the work Hubble is doing on exoplanet atmospheres. So the first exoplanet, that is the first planet outside our own solar system, was discovered after the telescope launched. So this was not a science topic at the time the telescope was designed and launched. And now Hubble spends about 20% of its observing time looking at exoplanets. And Hubble is indeed the premier facility for studying exoplanets and their atmospheres, even though it's not the premier facility for discovering exoplanets. Hubble's not a survey telescope, but once other surveys find exoplanets, Hubble is used to follow them up. And the way Hubble does this work is shown by the artist impression at the bottom here. A planet, when it passes in front of its host star, when it transits in front of the host star, the planet and its atmosphere affect the light from this system that you see, and the variation in that light is measured with Hubble, usually through the spectrum, and that tells us something about the exoplanet and its atmosphere. So another advance with the telescope that has changed over time is the way we use the telescope, and that's really making the pursuit of those two science cases I just showed you more powerful, and this is called spatial scanning. So normally it's important to hold a telescope steady when obtaining an exposure of an object, whether you're obtaining a spectrum or you're looking at an image of stars. What we do with spatial scanning is we intentionally drag the telescope across the field of view. And so if you're looking at a group of stars, as what I'm showing here in the top image, the stars create streaks during your exposure. But this works to the advantage of the astronomer, because now you're getting high precision astrometry and parallaxes for the objects in the field, because instead of getting one measurement for the position of each star, you're getting hundreds of measurements as those stars are dragged across the field of view. So you can get very high precision measurements of their relative positions. Along the bottom, I'm showing another way of using spatial scanning, and that's with spectroscopic observations. So this is exoplanet observation I'm showing here over the course of the exposure. Wavelength runs from left to right, and then the spectrum during the exposure is dragged across the detector from the bottom to the top. And because we're spreading the detector over a larger area, more signal can be detected before we saturate the detector, and we can average out systematic errors, and that allows a much higher accuracy to be obtained with the spectroscopic data. So next I'm going to explain in a little more detail this cosmic expansion and how this kind of work is pursued with Hubble. And one of the first ways that's being done is by combining observations of supernova explosions. So these are exploding star systems, and the brightnesses of those supernovae are calibrated with Cepheid stars, and these are stars with a known brightness. So first I need to explain the concept of the standard candle. So a standard candle is an object with a known intrinsic luminosity, and then when you observe that object at a particular brightness, that tells you something about how far away it is. So if I'm standing in front of you with a candle and you see how bright it is, and then I walk away into the darkness, it looks like it's getting fainter due to me being further away, and you can use that information to judge how far away I am. So that's a standard candle. Parallax is another phenomenon that we see here on Earth in everyday life. So if you're driving your car and you're going down the road and you see trees outside the window nearby, they seem to be moving relative to the background, for example, relative to a distant mountain range. And so as an observer looks at nearby objects as they're moving, that causes nearby objects to appear like they're moving against a screen of distant objects. And astronomers do the same thing with the Earth going around the sun. Over the course of the year, as the Earth goes around the sun and Hubble is going around the Earth, nearby stars appear to move relative to distant background objects. And that geometry allows astronomers to measure the distance to those nearby objects. So the same thing happens here with the measuring of the expansion of the universe. So this cartoon demonstrates that. On the left-hand side of the cartoon is a schematic of the Milky Way galaxy, and there's the sun with Hubble and the Earth going around the sun every year, and it's looking at nearby Cepheid stars and obtaining their parallaxes from the motion around the sun. So that geometric distance tells us how far away the Cepheid stars are, and then that allows us to calibrate how bright they are and make them into a standard candle. Those Cepheid stars are then observed in nearby galaxies in the local universe. That's shown in the center of the cartoon, and that allows us to calibrate the distances to those galaxies. Then when a supernova explodes in those galaxies, we know the distance to those galaxies, so now we know the brightness of the supernova. And now the supernova is a standard candle, but it's a much brighter standard candle than the Cepheids. It can be used at much greater distances. And so now the supernova are observed at extreme distances across the universe in distant galaxies, and that's what's shown on the right-hand side of the cartoon. And that allows us to measure distances of galaxies receding away from us in the distant universe. So it's a chain of evidence here working your way outward. And just to summarize that, so this method combines using two types of standard candles, Cepheid variable stars, and then type 1a supernova stellar explosions. And those are calibrated in turn, and then you can measure the expansion of the universe. And for example, Reese et al. Did this most recently and obtained a Hubble constant, h naught, and that's a measure of the expansion of the universe, of 73.2 plus or minus 1.3 kilometers per second per megaparsec. So a megaparsec is a little over 3 million light years. So that means for every megaparsec out you go, the recession velocity is increasing by 73 kilometers per second. So that's, you can see in the uncertainty there is quite small. Now there are other ways of measuring the expansion of the universe. So the Planck satellite, for example, is a mission that is mapping the cosmic microwave background. This is relic radiation left over from the Big Bang that is all over the sky, and it makes these all sky maps that are shown here on the left-hand side of the diagram. When you measure the ripples in the cosmic microwave background, that gives you an estimate of how fast the universe is expanding. And the Planck team, they measured a Hubble constant of h naught of 67.4 plus or minus 0.5 kilometers per second per megaparsec. And given the small uncertainty there, that's significantly different than the expansion rate measured from supernova and Cepheids, which is 73.2 plus or minus 1.3. These two measurements are significantly discrepant with each other. Now, the Planck measurement is looking at the relics left over from the Big Bang and working forward from that. The Cepheid and supernova method is looking in the nearby universe and working outward. So maybe that's the source of the discrepancy here. They're both coming at the problem from different angles, and that somewhere along the line there's new physics at work that caused the disconnect, and that's still under investigation. There are complementary programs exploring the cosmic expansion using different methods. So this is using what's known as a color magnitude diagram. If you measure the brightnesses and colors for a group of stars, those aren't random. This is a plot here of brightness on the y-axis and color on the x-axis for a group of stars. And you can see that it traces out a particular pattern. Dwarf stars like our own sun fall near the bottom of this diagram. Those stars, like our own sun, eventually swell up and become red giant stars, so towards the upper right of this diagram, until they reach the tip of the red giant branch, the brightest red giant branch stars. And those are a standard candle. So what Wendy Friedman's team is doing here is using Hubble, these are Hubble images shown on the right here, looking at nearby galaxies in their outskirts for bright red giant branch stars and measuring all the brightnesses of the red giant branch stars in those outskirts of those galaxies. And because it's a standard candle, the red giant branch star, that gives you a distance to these galaxies. And then when supernova go off in those galaxies, you have a new calibration for supernova. And now the rest of the technique is similar to what I just showed you in the last slide. But this is a different way of calibrating supernova as standard candles, using red giant branch stars instead of Cepheids. And using this method, Friedman et al. Found a Hubble constant of 69.8 plus or minus 1.9 kilometers per second per megaparsec, which falls between the two measurements I mentioned previously. A completely different way of coming at this problem is with gravitational lensing. So this is a little bit of a trickier concept. What I'm showing you here on the left are 4 images with Hubble of a gravitational lens system. And what a gravitational lens is you have a massive object with a strong gravitational field in the foreground, and then some background object that appears distorted on the sky because the light is reaching us through that gravitational lens. And so I can demonstrate this schematically. Here's the observer, the Hubble Space Telescope. We're collecting data with that, and we're looking out into the distant universe at a foreground lensing galaxy. So this galaxy acts like a lens because its gravitational field is so strong that the space-time is significantly curved around that galaxy. You have a distant background object, a lensed quasar. So quasar is an active galaxy in the distant universe powered by a supermassive black hole. It often has variations in its light. And the light from that quasar can reach us along different paths because of the lensing here. So it can go along this path I've shown schematically by path A here. It bends around the lens because of the gravitational field of that foreground galaxy. And then we're looking backwards along that sight line, so we see the lensed quasar image offset on the sky along that dotted line there. Light can also take path B here along this curved path. And again, we look back along the sight line, and the dotted line says this quasar image appears offset in the other direction. And this is how you can get multiple images of the same object on the sky. And that's what's shown here in the lower left. If you see the Hubble images here, there's a yellow object, that's the lensing object, and then the white objects around it are all the same object, but they're appearing offset on the sky because of this lensing effect. And this is just from nature and gravity. So this actually gives you enough information to constrain cosmology, because the light is traveling to us from the quasar along those different paths, and it takes different amounts of time to reach the eye because those paths are not the same length. And in this example here, the light travel time can vary by about 10 days or so. So there's enough information here to actually solve for the cosmology. Use high-resolution Hubble images to model the gravitational lens system. And then you monitor those different images of the quasar on the sky and look for flickering in those images and variations in the light. And if you see one change happen in the light with one image, and then it happens 10 days later in the other image of that quasar, that gives you a sense of the time delay along those two different paths. You combine that information and constrains the geometry of space-time. Wang et al. In this example here used such measurements to get a Hubble constant of 73.3 kilometers per second per megaparsec, which is very similar to the first case I showed you with the supernova and the Cepheids from Rees et al. Now, the Hubble Frontier Fields is a program with Hubble that really delved into this gravitational lensing effect. This was a director's discretionary program of 840 orbits. The director of Space Telescope gets a pool of orbits every year that can be applied towards large programs that benefit a large area of research in the field. And that's what was done here. It was 840 orbits and was used to observe 6 massive galaxy clusters, which are shown in the 6 top panels in this figure here. And because we have 2 cameras on Hubble, while one's looking in the galaxy cluster, the other one is looking in a nearby empty field, a parallel field, so those are shown along the bottom. And the research you can do with this is really amplifying what's possible with Hubble due to the gravitational lensing. So the lensing enhances Hubble's reach because galaxies can be magnified by up to a factor of 50. Hubble can detect galaxies 10 times fainter than otherwise possible. And in the work here by Rachel Livermore, she used this lensing to see into the distant universe and look at the role of faint galaxies in the evolution of the early universe, and demonstrated that they had a significant role in the reionization of the early universe. So here are the lensed images again for all 6 galaxy clusters. Now, as I mentioned, if something happens, if there's a variation with one of the lensed objects, as I was talking about the quasar earlier, because the light takes different paths to get here through the lensing system, you might see the same event happen multiple times. And we were actually lucky enough to have that happen in one of these galaxy clusters. A supernova that was lensed occurred. So a star system exploded one time, but we got to see that explosion multiple times. And so that was in this one system here. It turns out that the supernova, if we had been looking, would have been first visible in 1995. That was the earliest the light reached us, but no one was looking at that time. So that's shown here. That happened there. But then in 2014, we saw the supernova occur in a lensed image, and modeling of the lens system implied it would happen again, and indeed it was observed to happen again in December of 2015, just in line with the predictions. And if you combine the measurements, similar to the method I showed you before with Wang et al., this team who looked at these data first, shown in the bottom of the slide here, obtained an expansion rate of the universe of 64 kilometers per second, which is a little lower than some of the other measurements I mentioned earlier, but the uncertainties are significantly larger. It's roughly plus or minus 10 kilometers per second, so it's still consistent. Now I'm going to switch gears here and talk about the other topic I mentioned in the beginning, which is exoplanet science. So exoplanet science began in the 1980s. That's with this image here on the left, the Beta Pictoris system. Now, in this image from the Las Campanas Observatory, what was seen once the telescope was used in a way employing a coronagraph to block out the central light and see the objects, the fainter objects around the bright star, what was seen was a planetary disk, so a baby solar system being born. And so this, although this didn't show us planets, it showed us a protoplanetary disk being born in this system. Hubble launched in 1990. At the time, there were no known exoplanets. The first normal exoplanet that was discovered is this system 51 Pegasi, and it wasn't done through imaging. It was done through what are known as radial velocity measurements. So what's being plotted here is the velocity variation in this star along our sight line, so a radial velocity, as the star is wobbling due to the tugging, the gravitational pull of a planet orbiting that star. And so this is just a change in radial velocity as a function of time over and over again is what's being shown here over the cycles of that planet orbiting its star. So that was in the mid-90s after Hubble launched. Hubble did play a role in what's currently known as the oldest known exoplanet. And this is a system that has a story that goes back over a number of years. So what I'm showing in the center here is an image from Hubble of the globular cluster M4. A globular cluster is a swarm of old stars, roughly 13 billion years old, about 100,000 stars or more. And in this globular cluster, in the late 80s, a binary pulsar was discovered, not using Hubble. This is before Hubble launched. A pulsar is kind of like an astronomical lighthouse. It's a collapsed neutron star that's spinning very rapidly and sending out a beam of energy into the universe over and over again with a repeated signal. In the early 90s, multiple papers were published showing that this pulsar had a timing anomaly, and that might be indicating the presence of a Jupiter-mass planet in the system. In the late 90s, radio observations gave more evidence that there was a planet present. And then in 2003, astronomers used those data plus several years of Hubble imaging to conclusively demonstrate that there was a planet in the system. And that planet was 2.5 times the mass of Jupiter, and it was actually a triple system. And given where this was, it's a triple system 13 billion years old. So this is the oldest planetary system. This plot at the bottom, I'm showing from Sarah Seeger, demonstrates the difficulty in doing exoplanet science. It's a plot of the energy of an object versus the wavelength in microns for different types of objects. At the top is in yellow is the spectrum you get from a sun-like star. So a star like our own sun. The y-axis here is logarithmic. So as you move down this scale, things are changing by an order of magnitude, by factors of 10. And so as you go down to the hot Jupiter here, the next lowest object, the dotted line, that's what you would see for a Jupiter that's orbiting very close to its host star, so a hot Jupiter. And you can see its orders of magnitude fainter than its star. And then other planets that we see in our own solar system, like Jupiter, Venus, Earth, and Mars, their orders of magnitude fainter still. So this is the trickiness of trying to do exoplanet science, which is that exoplanets are very faint objects, extremely close to much brighter objects, their host stars. And so you need to try to mask the light from that bright star if you want to see the planet, or you have to look at the effects of that planet on its host star, the light from that host star. And that it requires a very careful measurement since the planets are so much fainter than the host star. This diagram now here in the lower right, this is a plot of the number of known exoplanets over the lifetime of Hubble, going back to 1990 to the present. And you can see when Hubble launched, there were no known exoplanets. And today we know of thousands of exoplanets. And the different colors here are the different methods for discovering exoplanets. As I said, Hubble is not used generally to discover exoplanets, but it is used to follow them up. So I'll go through some of the highlights of Hubble's exoplanet work here over the years. So Hubble was used for the first detection of an atmosphere around an exoplanet. This was done with the STIS spectrograph, shown by the artist rendition here in the middle. And what was done here is that STIS observed this exoplanet system during 4 orbits of the planet and around its star. We obtained data like that shown here on the right. This is the spectrum, so variations in energy versus wavelength on the x-axis in microns. Those little wiggles in the black data points there are from the variations in the chemistry of this atmosphere. And we've highlighted the sodium feature in gray there. The sodium feature in this spectrum over the course of these observations varied significantly due to the fact that as the planet passed in front of the star, the sodium in the atmosphere of that planet changed the sodium feature in the spectrum. So this was the first exoplanet atmosphere found in another star system. This star has a spectral type similar to the Sun, and the planet has a mass similar to Jupiter. This is the first detection of an organic molecule in an exoplanet atmosphere. This was done with the NICMOS instrument, which is still on board Hubble, although it's no longer operational. What was performed here was using NICMOS, observers watched the planet transit in front of its star and then go behind its star, the secondary eclipse. And the variations seen in the spectrum over the course of that time there was consistent with methane absorption in the exoplanet atmosphere. So in the center bottom of the diagram here, you can see the variation in light over time at different wavelengths as the planet passes in front of its star. And the lower right are the spectroscopic data. This is a plot of absorption versus wavelength in microns. The black points are the Hubble data, and then the curves in orange and blue are different models for what can be happening in the atmosphere. And you can see the orange model, which has the right amount of methane, agrees well with the black points, indicating there is methane in the atmosphere of this exoplanet. This is Hubble a few years ago now. This is more recently, using the spatial scanning technique I mentioned earlier, where we intentionally drag out the spectrum over the detector to obtain more signal and get a more refined signal for the exoplanet. So this enabled the observation of simultaneous transits of 2 Earth-sized exoplanets around their host star. That's what's shown by the artist rendition here. This planets are TRAPPIST-1b and 1c. This is the TRAPPIST system. The data from Hubble are shown in the bottom. Again, this is changes in energy or flux versus wavelength. So these are the spectra. The black points are the data points from Hubble, and then the different colored curves are different models for what's happening in the atmosphere. And the best agreement comes when you minimize the amount of helium and hydrogen in the envelopes for these exoplanets. And so that means these exoplanet atmospheres have little hydrogen and helium and increases the odds that they're habitable. Finally, I'm showing you here a more recent result from Hannah Wakeford. This is the most detailed look at an exoplanet atmosphere to date. It combines data from 3 different telescopes: Hubble in space, 2 of its instruments, the Very Large Telescope on the ground, 1 of its instruments, and then the Spitzer Space Telescope, 1 of its instruments. And you combine all those together, you get the spectrum, the composite spectrum on the upper right there, shown on top of an artist rendition of the planet. This is a plot of the signal strength on the y-axis versus microns on the x-axis, wavelength in microns on the x-axis. And the different wiggles in that spectrum are due to the chemistry of the exoplanet. So you can see hydrogen, helium, sodium, potassium, water, and carbon dioxide. So this system, the planet here is called WASP-39b. It's thought to be a hot Saturn orbiting a sun-like star. The spectrum shows clear evidence of water in the atmosphere at triple the abundance of that in the Saturn of our own solar system. On the bottom here now, I'm going to demonstrate why combining data from all these different wavelengths and different facilities is so powerful. So first we're showing you here in purple just an analysis done on the near-infrared data alone. So on the bottom right here is a spectrum showing the absorption on the y-axis versus wavelength on the x-axis in microns, and the black data points are just the infrared data. The purple curves that are passing through the black points, that's the full range of models that is consistent with those data. On the lower left are 4 panels showing the properties of interest for this exoplanet system. We'd like to know its temperature, the metals present, the radius of the planet, and the haze in the atmosphere. And there are a lot of values that are consistent with the data. That's why there's a distribution in each of those plots. If we, however, combine now all the data available to us from the ultraviolet, the optical, and the infrared, that's what's shown now in green. So the black points on the spectrum at the bottom right here, now the black points are the data from all the different telescopes being combined over a wide wavelength range. And because we have more data points in black, the curves now for the model, which are now shown in green, are much tighter. There are far fewer models that are consistent with the data. And that's shown here by the constraints on the left. So now here are the 4 properties again of the exoplanet atmosphere we're interested in: temperature, metals, radius, and haze. And now the distribution is much tighter. And if you see, if I blink back and forth, in purple here's the wide, where we don't have as good a handle on things because we're not using all the data. And now things are narrower because we are using all the data available and we get much better constraints. And so looking ahead, this is giving us a lot of hope for the 2 telescopes working together when James Webb is up in space. The James Webb Space Telescope is launching later this year. It's primarily an infrared telescope. And when it's working in tandem with the Hubble Space Telescope, when those two telescopes are working together looking at exoplanets, we're going to get amazing constraints on their atmospheres. Now, it's not just other solar systems that Hubble observes. Hubble spends a significant amount of time looking at our own solar system, and in particular supporting other dedicated missions throughout our solar system. So, for example, the New Horizons mission navigated to Pluto, and Hubble played a key role in navigating to Pluto, identifying 4 new Pluto moons, and also confirming that the navigation pathway for New Horizons was safe from debris. And then once New Horizons arrived at Pluto, Hubble was used to identify a target for an extended mission for the New Horizons mission, Ultima Thule, and provided navigation assistance to proceed to that target. And so the center image shown here from Hubble is the extended mission target, and on right is the image obtained from New Horizons as it reached closest approach to that target. Hubble has looked at Jupiter over the years. This is a relatively recent image from 2020 of Jupiter, beautiful color image. And there are also missions to Jupiter. So for example, the Juno spacecraft, which is shown not to scale on the upper left there, has been orbiting Jupiter with a period once every 53 days of approaching Jupiter's closest approach. And when the Juno satellite orbiting Jupiter reaches closest approach to Jupiter, at those times, Hubble is looking at the same time, contemporaneously, to provide data alongside the Juno data, as are telescopes on the ground, such as the Gemini telescope. And so working with multiple facilities together, we get new insight into the physics of what's happening on Jupiter. And for example, here are the storm systems on Jupiter. So the Juno satellite is peering into those storm systems in radio waves. The Gemini telescope is looking in the thermal infrared, and Hubble is looking in reflected light. And by combining data from all of those facilities working together, we can get new insight into the storms on Jupiter. And we also, besides looking at other star systems for their exoplanets, we look at other stars to understand star formation history in the universe. This is something called stellar archaeology. When you look at a group of stars, such as that shown here, this is a beautiful Hubble image of a crowded star field, you see a distribution of colors and brightnesses. The colors reflect the temperatures of those stars, and the brightnesses reflect the luminosities of those stars. But that distribution is not random. The distribution you see traces the life cycle of a star, traces stellar evolution. And the picture you see here will change with age. And Hubble can use this kind of information to probe the detailed history of star formation in both nearby galaxies and nearby star clusters, where we can resolve the individual stars like this. And so I'm going to show you an animation put together by some folks, shown at the bottom there, their names, at Space Telescope, who put together this animation of this Hubble image. We're first going to sort the stars in color left to right, with the hottest, bluest stars on the left and the coolest, reddest stars on the right. Then we're going to sort the stars in luminosity, with the brightest stars at the top and the faintest stars at the bottom. And what you get here, sorting the stars in that Hubble image, is a color magnitude diagram, such as the one I showed earlier in the talk when I was talking about the red giant branch as a distance indicator with the cosmological measurements. So you can see here the distribution is not random. There's this pattern, and dwarf stars are near the bottom of this diagram. The sun is a dwarf star, and dwarf stars will swell up and become red giant stars towards the upper right. And the tip of the red giant branch are the brightest red giant branch stars up there at the upper right. Those stars then ignite helium in their cores and become much hotter. So they move over to the upper left part of this picture here, where you see the bright blue stars. They're hotter and blue bright stars. And then when they exhaust their fuel, they fade as white dwarfs to the lower left. So that's the story that's told by the distribution of color and brightness in a Hubble picture. And Aline Tolstoy demonstrates this well here in this figure. She's done a lot of work in this area with a variety of telescopes. And what's plotted here in her plot is brightness on the y-axis versus color or temperature on the x-axis for different evolutionary phases in the life cycle of a star for stars of different masses. And they're color-coded here according to the table alongside on the right. So for the most massive stars, we call those O stars, they have a mass more than 100 times the mass of the sun. They go whipping through this diagram very quickly on a timescale of just a few million years. And then for low mass stars, such as an M dwarf star at half the mass of the sun, it takes billions of years to go through this diagram, to evolve through this diagram. And so all the different masses of stars in a group of stars evolve at different rates, and we can trace their evolution in this distribution of brightness and temperature. Now, to give you a specific example of this type of research, this is an image, a photograph taken from the surface of the Earth of the dark night sky. And for those of you who've been able to look at the sky away from the cities, out in the woods or out where it's quite dark, you can see the strip of stars going across the sky that's called the Milky Way. That's our own Milky Way galaxy. We live in a spiral galaxy, and the disk of that spiral galaxy is where the sun resides. And because we're in that disk, it forms a stripe of stars that goes across the sky if you're out someplace where it's dark enough to see it. What's shown by the inset is the center of the Milky Way, where we pointed with Hubble. And so that inset there is the high-resolution Hubble image of just one tiny piece of this much larger photograph zoomed in on the center of the Milky Way. That field is called the Sweeps field. The acronym is the Sagittarius Window Eclipsing Extrasolar Planet Search. This is a program led by Kailash Sahu nearly 20 years ago. He pointed Hubble at this star field, this crowded star field, for a week to look for exoplanets. And he successfully found the most distant exoplanets found by transit. When those exoplanets passed in front of this crowded field of stars, it affected the starlight from those stars that we measured, and we were able to find exoplanets. However, this star field is itself interesting because it gives insight into the formation of the center of the Milky Way, our galaxy. And this field has been imaged repeatedly by Hubble over the years. And because it has both excellent detail in terms of the colors and brightnesses we measure, but also a time series of being looked at repeatedly over the years, this gives us both insight into the star formation history, but also the motions in the center of the Milky Way. And so just to demonstrate that, here's the high-resolution image from Hubble. Again, this distribution of color and brightness is not random in here. And I'm going to zoom in on one patch in the upper left here, pull that over to the side, and if you look very carefully at your screen, you can see that the stars are moving. This is 2 years of Hubble data turned into a time lapse. It's just playing back and forth over the loop, frontwards and backwards. So you can see the motion of stars. So this is not an animation or an artist's rendition. That's the actual series of Hubble images at one wavelength and one filter on Hubble at that patch of the field. And so you can see the motions of the stars, and you can see the ages of the stars. And so Will Clarkson recently had a press release on these results where he found 2 distinct populations of stars based on these data in the center of our Milky Way. He found an older population that was less chemically enriched. These stars were moving more slowly, and they were probably there in the early part of the Milky Way history. And then he found a younger population of stars that was more enriched, moving more quickly. These were probably in smaller galaxies that were cannibalized as they fell into the Milky Way. Now, Hubble also has a very large program underway right now to produce a library of stars for the future. This is another director's discretionary program like the Frontier Fields I mentioned earlier. This is 1,000 orbits spread over 3 years. It's called the Ulysses program, the Ultraviolet Legacy Library of Young Stars as Essential Standards. And what this program is doing is creating a spectroscopic library of ultraviolet spectroscopy that can be used by other telescopes now and in the future, because this is a unique Hubble ability, and it's going to be a legacy for Hubble. So the library is going to be looking at young stars at a variety of masses, sampling different parameters for stars. The survey was put together with the participation of the scientific community. They provided initial input for the design of the survey, and then they continued to provide advice. The implementation team at the Space Telescope Science Institute is led by Julia Roman Duval. And so this is another one of these stellar diagrams with brightness on the y-axis and color or temperature on the x-axis, and it's showing the evolution of young stars at different masses, ranging from half the mass of the sun to 15 times the mass of the sun. And they take different tracks through that diagram. The Ulysses program is spending about 500 orbits looking at the most massive stars in this diagram. And this is a beautiful Hubble image of such massive star formation. And then it's also looking at the low mass stars in this diagram, and this is a Hubble image of such a star. This program, though, is producing spectroscopy, not images, so it's producing spectra like what's shown here in the middle of your screen. This is the ultraviolet spectrum, so energy versus wavelength in angstroms for a high mass star, and it's showing features from different aspects of the chemistry and physics involved. In blue is highlighted an absorption feature from the dark interstellar medium between the stars. In green, there's a feature from the stellar wind in the star. And then in red is highlighted a feature from the dark circumgalactic medium between the galaxies. So for high mass stars, we're going to be doing giving a look into the winds, chemistry, and radiation for stellar astrophysics. And we'll be looking at the interstellar and circumgalactic medium between the stars and between the galaxies. And then for low mass stars, we're going to be looking at the physics of those low mass stars, the accretion that happens, the shocks, flows, disks, and jets, and their transient activity. Now, as I mentioned, the dark material between the stars is also an area of study, and it was actually that kind of science was a prime motivation for the cosmic origin spectrograph, one of the two spectrographs on Hubble. And the way this science works is shown schematically in the lower left here. The material between the stars is dark. It's gas and dust. It's not luminous. And so the way you measure that material is look along a sight line through the universe at some background illumination. Basically a flashlight that nature provides. And you look back towards a quasar, is what's commonly done. So that's what's shown in the schematic here. Hubble is looking through the dark material in the universe back towards a quasar. A quasar is a quasi-stellar object. It's an active galaxy nucleus powered by a supermassive black hole. And these are bright. As they give off the light passes through the universe, comes back to Hubble, and then some of that light is absorbed on the way to Hubble because of the circumgalactic medium. Two recent examples of large Hubble surveys in this kind of work. There's the CUBS survey led by Chen et al. This is the Cosmic Ultraviolet Baryon survey. Chen is looking here, her and her team are probing the circumgalactic medium toward distant galaxies at intermediate redshift, looking back in time roughly 4 to 10 billion years into the past to probe the chemistry of the circumgalactic medium over a fairly large distance here. And then there's the Amiga program, Absorption Maps in the Gas of Andromeda. This is led by Leonard et al. This is probing the environment around the nearby Andromeda galaxy. That's a giant spiral galaxy like our own galaxy. It's the nearest spiral galaxy to our own in the local neighborhood. And this program is intended to investigate the vast halo of gas around Andromeda. Now, Andromeda, because it's the nearest spiral galaxy and it's similar to our own in many ways, it's been the subject of study to many astronomers over the years, and Hubble has spent a lot of time looking at it. And just to give you some background on that, there is the pan-chromatic Hubble Andromeda Treasury led by Julianne Del Canton. This was a very large program spending hundreds of orbits mapping a significant part of Andromeda. So what's shown here on the right now is a ground-based image of the Andromeda galaxy, the entire Andromeda galaxy, which is quite large on the sky. Again, it's a spiral galaxy like our own. It's somewhat edge-on, not entirely edge-on. And then the section that's highlighted where it says HST FAT, that's the map that Julianne Del Canton performed, that she obtained with Hubble, taking Hubble and tiling out in great detail with Hubble's cameras a significant chunk of the Andromeda galaxy in the ultraviolet, optical, and near-infrared, making a high-resolution map of that part of the galaxy. I'll zoom in here. Here's a more detailed look at the map that the FAT program obtained. And just to give you a sense of scale, everyone knows what the full moon looks like on the sky. So this is how big that patch of sky looks like compared to the full moon when you go outside. And I'll zoom in on one section here just so you can see that Hubble is able to resolve individual stars in the disk of Andromeda here and disentangle the star formation history of Andromeda. So now I'm going to pull back out. Like I said, a lot of work has been done on the stars of Andromeda. What this Amiga program has done, though, is zoom much further out than this. So I'm going to pull much further out. This is to scale now. The full moon would be tiny on this scale, hard to see. And the Amiga program probed various sight lines through the vast plasma halo of Andromeda, around Andromeda, looking at background quasars. So these orange circles that are shown here are each a sight line to a background quasar behind Andromeda, and looking through that sight line at each of those quasars to see the absorption from the halo of gas around Andromeda. And the results demonstrated that this halo of gas around Andromeda extends at least 1.3 million light years in all directions from Andromeda. And what's amazing about that is Andromeda itself is about 2.5 million light years away from the Milky Way, our own galaxy. So the fact that this halo extends 1.3 million light years in all directions means it extends more than halfway back towards us. And there are at least two distinct shells of complex gas in the halo of Andromeda, in this gas, as can be seen here by features of carbon and silicon in the spectra that are obtained. So these halos are quite complex, the shells around this galaxy. Now, as I said, each of these sight lines is illuminated by a background quasar. A quasar is a distant active galaxy nucleus powered by a black hole, and black holes are also the subject of intense study with Hubble. So I'll show what really got this kicked off was an observation of M84 in the late 90s with the Space Telescope imaging spectrograph. STIS is able to provide spatially resolved spectroscopy. So what's shown on the far left here is an image of the galaxy M84 with one of the earlier generation cameras on Hubble, Wide Field Planetary Camera 2. And then STIS placed its slit in the center of this galaxy along where the black hole is and produced the spectrum you see here. So what is being plotted is the velocities implied by that spectrum as a function of position along the slit. So green is a velocity similar to the velocity of the galaxy. And as you move along the slit, the velocities shift dramatically over to the blue. And then they move, and that's a Doppler shift because things are blue shifted. And then they shift all the way back to the red again before returning to the velocity of the galaxy. So the blue is material that's falling towards us. It's material on the far side of the black hole falling into the black hole towards us, so it's blue shifted. And then the red is material on the near side of the black hole falling away from us into the black hole, and so it's shifted to the red. And that velocity that is implied by this motion is a velocity of 400 kilometers per second at a point 26 light years out from the center of the black hole. And it implies a black hole mass of more than 300 million times the mass of the sun. And once Hubble did this, Hubble continued to look at many black holes in the nearby universe over the years since then. So for example, here's a much more recent result in 2019, looking at a spiral galaxy, NGC 3147. The Hubble image is shown on the left. In the center is an artist's rendition of its black hole. And on the right is a spectrum of the material in the vicinity of the black hole. The black curve is the Hubble spectrum, and in red is the model of the material falling into the black hole. The data shown here imply that there is a supermassive black hole of around 250 million times the mass of the sun, and also shows that this material around the black hole is in an accretion disk that's moving at relativistic speeds at about 10% the speed of light, and the accretion disk encroaches closer to the black hole or event horizon than what's predicted from theory. Now, as I said, Hubble has looked at many black holes over the years, and if you look at the ensemble of black hole measurements made to date, you can see that black holes are intimately related to their host galaxies. So what's shown here in the upper right in this plot is the mass of various black holes in units of masses of the sun on a logarithmic scale there. And then on the x-axis is the galaxy mass for the galaxy where those black holes reside, again on a logarithmic scale in units of the mass of the sun. And you can see that the two are correlated. They're tightly correlated there, and thus the black hole mass tends to go up when they live within a galaxy of higher mass. And so black holes are tied to the evolution of the galaxy within which they live. Now, Hubble more recently is starting to look at other explosive phenomena in the universe, like gravitational wave events. These are ripples in the space-time continuum caused by the merger of massive objects, and one that got a lot of attention with the press several years ago is this merger of a binary neutron star system. So a neutron star is a collapsed dense star near the end of its life, and there was a binary neutron star system where the stars were spiraling around each other and eventually merged, and that caused a gravitational wave event that rippled out throughout the universe, and was detected by two gravitational wave experiments, the Advanced LIGO experiment and the Virgo experiment, in August of 2017. There was a gamma ray burst detected from this event also at the same time by two experiments, and a bunch of facilities were all following up on this, and the event was localized to the galaxy NGC 4993 at a distance of 40 megaparsecs. Hubble and other observatories provided follow-up in the days and weeks afterwards. That's what's shown here on the left is the Hubble imaging of this event in the aftermath over the course of several days, or what the insets that are shown there. And then also Hubble, by chance, happened to observe this same galaxy by luck several months before the event in April of 2017. So we also got to see what this galaxy looked like before the explosion happened. Hubble will play a critical role in this type of science in the 2020s as more gravitational wave experiments come online and they become more sensitive, and there are additional all-sky surveys with a variety of facilities. All of these surveys, both gravitational wave experiments and all-sky surveys at other wavelengths than Hubble, are going to be scanning the sky and finding new explosive transient phenomena, and UV optical follow-up data with Hubble will be key because Hubble has unique capabilities, and it'll help provide localization within the host galaxy for these events. It'll provide high precision positions and luminosities. It'll also provide discrimination between competing models of the transient event. And just to show you how it can do that, what's plotted here is from this gravitational wave event in 2017 is a plot of the brightness versus time in days at different wavelengths. So in the purple colors, that's ultraviolet light, and then the red colors, that's infrared light. And this is from a variety of data sets looking at this gravitational wave event over the course of several days and weeks. And you can see in the ultraviolet, the gravitational wave event fades quite quickly, whereas it takes weeks to fade in the infrared. And so this strong wavelength dependence to the decay will give us insight into competing models of the physics of what's happening here. So Hubble's outlook for the 2020s, Hubble will play an exciting role in the next decade of astrophysics. Hubble and Webb working together will give us amazing insight into exoplanets and their atmospheres. Hubble will continue to probe the expansion of the universe and the dark energy responsible for it. Hubble will work with solar system missions exploring our own solar system. And Hubble data will be key to understanding the data obtained of other upcoming survey facilities. Those survey facilities are going to be exploring transient explosive phenomena. We're going to have a new decade of all-sky surveys and also gravitational wave astronomy. And Hubble will be involved in all of that. Thank you.
Thank you, Tom. That was great. I mean, that is, it takes a lot to cram into an hour, all the things that Hubble has done for 30 years. How long have you been the HST mission head?
Since 2016. I worked on James Webb for 8 years before that, and then Hubble before that.
Right. So you've seen quite a bit of some of the new stuff that we've been able to do. And so I guess one of the questions I would ask is, in looking at how Hubble has changed over, how we've used Hubble over the years, you showcased the drift scanning. Are there other really cool things that we've been able to do with Hubble that we didn't really imagine that we were going to do from the beginning?
I mean, the exoplanets is the most obvious thing, and it really captures the imagination because the whole search for life, it's really laying the groundwork for the eventual discovery of life in other systems. That's one of the holy grails of astronomy. So I would say that the high precision measurements that we're doing with astrometry, that, again, I highlighted this early in the talk, that was not really foreseen at this level when Hubble launched. We knew that Hubble was going to give us really amazing detail and high contrast, high resolution imaging that would allow us to measure positions and motions of stars. But with this drift scanning, as we said, now that we can do, it's orders of magnitude more powerful than we thought we would be able to do at launch. And it's competitive with dedicated missions. I mean, the Gaia mission is doing amazing work in this area over the vast sky, but Hubble gets measurements that are competitive with Gaia in this area and is actually used for specific ways to complement what Gaia is doing. So, I mean, as the field changes, Hubble gets used in new innovative ways to complement the field, and complement work with other facilities.
Right. And that's one of the benefits of having a telescope, that you learn and relearn and adjust for 30 years.
Right.
So we actually had a question about that in our chat. And it said, how do you line up multiple exposures so precisely? I mean, Hubble's orbiting and it's got to be wiggling and wobbling and such. And can you explain a bit about the FGS stuff?
Sure, yeah. So the pointing control system involves multiple components that are all working together. And when we're actually looking at an object, we have 3 operational gyroscopes that are helping to orient the telescope. And then we also have what we said was the fine guidance sensor package. And these are 3 fine guidance sensors that we also call the pickles. They have sort of a pickle-shaped view on the sky that extends a much wider field of view than you get on the normal cameras on Hubble. And matter of fact, you can look on the web. I don't have one handy in the slides here, but you can see the focal plane of Hubble and where all the different cameras look. And then the pickles are this very obvious 3 pickle-shaped fields of view. And what they do is they look at a big group of stars that fall into the pickles and just track where those stars are within the field of view of the fine guidance sensors. And you have those working in tandem with the gyroscopes, and then the reaction wheels can orient the telescope, and all those work together very carefully to hold things steady at the level of milliarcseconds. I mean, so it's a system that all works together, dovetails together very precisely.
Right. I don't think people recognize that. They sort of think it's just the gyroscopes doing it all,
Right.
and getting that feedback loop between all the different systems is so important.
Right.
Okay, so we got some basic questions that we always get about Hubble, so I'll hit those first of all.
Sure.
Would another servicing mission be possible with, for example, the Falcon Heavy?
Right now, there are no servicing missions planned, but it is intriguing to watch the new variety of launch services coming online as the cooperation between both government space programs and commercial space programs, like SpaceX and Blue Origin and so forth. So it's possible that someday someone could service Hubble. I mean, right now, no one has mapped that out in detail, but yes, there are heavy lift capabilities coming into play. People have looked in the past at ways we could have, in the early 2000s, when the last servicing mission to Hubble was in danger of being canceled and not proceeding, people were looking at ways of doing Hubble servicing robotically, for example. So people have looked at innovative ways to service Hubble, and these new launch facilities coming online could certainly, revisit that question.
Okay. So the obvious question then is, without a servicing mission, how long do we expect Hubble to last?
So Hubble has already lasted much longer than we expected, and that's good news. So I'm not saying that, that means it can go any day. This is really a positive story, because during the last servicing mission, 2009, and I worked on one of the instruments, that Wide Field Camera 3. That's what I was working on right before I switched to James Webb. We were hopeful that Hubble at that time, after the last servicing mission, would last till about 2016 or so. That was really what we were looking for. But what happened was, after everything was up there and we saw how well everything was working, and we were able to track everything and watch the evolution of it as it was up there and in the harsh environment of space, we had to reevaluate those reliability estimates, because we said, oh, hey, a lot of the things that look like they could be wearing out, it's actually working much better than we thought. And so the engineers at NASA gave that all another look, and they continuously update the estimates for how reliable the different subsystems and instruments are. And right now, there's an excellent chance that we are operational through 2026. And every year we're operational, things look better and better. And so there's still a good chance it lasts throughout the 2020s. So, we'll see.
All right, so that leads to the other question that was asked, is about the capabilities of HST versus JWST. And then we just got a recent question about JWST and HST working together. So some people don't understand the different capabilities the two telescopes have. Can you just go into that for a little bit?
Sure. So first of all, James Webb is much larger than Hubble. It has a much bigger aperture. The width of its primary mirror is 6.5 meters across, whereas Hubble is 2.4 meters across. So there's a lot more collecting area for James Webb. And James Webb was designed primarily to look at very faint red objects in the far distant universe, looking way back in time, looking all the way across the universe. And so it's an infrared telescope. It has a large segmented primary mirror to collect this very faint infrared light. It doesn't really operate at short wavelengths into the optical and ultraviolet. And that's where Hubble really shines, because it's one of the only facilities that really, it's the largest telescope working in the ultraviolet and optical in space. And so what we're going to see is a shift, I think, after James Webb launches, where James Webb is really going to be pushing the envelope in the infrared. I think we'll still do infrared science with Hubble, but we'll shift what we're doing with in the infrared of Hubble, given the presence of James Webb. And then you're going to see things working in tandem, where looking at the same object like an exoplanet, James Webb will get the infrared data, Hubble will get the ultraviolet and optical data, and you'll combine those to really learn everything about that object that you can. And the exoplanets is a great example of where that really works well, but there are other areas as well.
Exactly, because your demonstration in your slides of why we need multiple telescopes in multiple wavelengths really showed, NASA doesn't need just one telescope. It needs a fleet of telescopes to cover as much of the electromagnetic spectrum as we can.
Yeah, and Hannah Wakeford, that was her research there. I had her name on the slide, but she's really given stupendous talks, if you look out there, on this subject about how synergistically combining exoplanet data from different facilities really breaks open, what you can learn. So.
Somebody asked, has Hubble ever been hit by space debris?
Yeah, so it gets hit by micrometeorites.
Not like the movie Gravity, by the way.
Yeah, right. Right. So it does, there's the environment of space is pretty harsh. So there are both cosmic rays passing through Hubble and bouncing around and causing scattering, radiation scattering. And then there's also micrometeorites. And so when the astronauts go up there every servicing mission, they've refurbished the outside of Hubble and the blankets and the surface of Hubble. And you can see impacts from Hubble, but it's not like something, has gone clear through it and done damage that is catastrophic in any way or anything like that. It's just you can see the impacts from micrometeorites, etc. Yeah.
Okay, and then we got a question that I'm not sure myself the answer how to answer this one. Do you think faint gravitational waves from the early universe will contribute to the cosmological constant or understanding of the cosmological constant and such? They're trying to take these gravitational wave discoveries and see, does this affect the universe on large scale with this the dark energy?
I mean, dark energy still remains a mystery, and as the uncertainties shrink on the measurement of this expansion, these groups who are doing this research begin to rule out some of the possible explanations for dark energy and the expansion of the universe. Given the variety of answers still on the table, I guess it's not unthinkable that the gravitational wave astronomy could help shed more light on that problem. No pun intended there, because there's really no light with the gravitational waves. But I suppose it could help narrow down what's going on. But I'm not a gravitational wave astronomer either, so I could just tell you that I've seen people looking at it in cosmic microwave background radiation and through these different chains of evidence of the expansion from local objects. Gravitational wave astronomy, might have a role to play.
Yeah. So. It's such a cool that we're getting these new ways of seeing the universe,
right,
popping up in our lifetime. Okay, last question I gleaned from the chat was about gravitational lensing. And it appears that this person is used to seeing gravitational lensing as forming rings, but when you showed them that they were the point sources,
right?
Can you just go into a little bit about that and how gravitational lensing can produce different imaging?
Sure. So if you actually make a map, and I showed in that one slide where that's where it looked like the video went off the rails for a little bit, and then I brought it back. So I guess people still saw those images, right? So there's actually a great paper on this recently that I just saw in the literature that explains this. But basically, the gravitational lens is the foreground object. And depending on how far away you are on the sky, projected on the sky, not physically how far away, but just the background object, where it falls on the sky relative to that massive lens, you get dramatically different effects. And so there are places where you can go, and the geometry is quite complex, where you get something like a ring, like you said. But then there are other places you can go where the light really is focused on one side or the other of the lens. And that's when you get these multiple images. And depending upon the structure of the gravitational lens itself, because often it's not just a single massive galaxy, it can also be a galaxy cluster with a complicated mass distribution in there. You can get quite complex patterns, and the frontier fields show great examples of that, where it's not just one lens, it's all these arcs, and a supernova exploded multiple times, even though it's this one supernova, which blew people's minds when they saw that. I mean, you knew it was possible, but to have that happen was like, get out the party hats, because it was really an amazing demonstration of both lensing and the time delays involved, right? So
yeah, gravitational lensing always attracts the public's fascination, and the number of ways for it to be complex has just multiplied with Hubble. And I remember when I was just starting with Hubble, and we got the image of Abell 1689, and seeing the tremendous lensing that Hubble could see, that Hubble's high resolution really has made that field just jump.
Right. Right.
Okay. Well, Tom, that was fantastic. Really great overview. I want to say to everybody, please join us next month, April 6th. Christopher Wanjak will be talking about spacefarers, how humans will settle the moon, Mars, and beyond. And thank you very much for watching.
All right, thank you.